Hi, in this video we will continue exploring the topic of harmonic oscillators, but this time we will introduce damping to make things more realistic. I previously made a video on the simple undamped harmonic oscillator where I covered some basic math that will be important for this video. So if you haven't seen it yet, I recommend checking it out first and then coming back here. You can find the link in the description. Alright, let's start by setting up the problem. We have a mass attached to a spring. On the left hand side the spring is attached to an immovable ball. And on the right hand side, there is an object of mass m attached to a spring. The spring is characterized by constant k, which we discussed in the previous video. I've placed the origin of the coordinate system at the equilibrium position where the spring is relaxed. So the x-coordinate measures the displacement of mass from its equilibrium position as a function of time. When x is 0, string is relaxed, when x is positive, string is stretched, and when x is negative, string is compressed. To describe the motion of the object, we need to set up the equation of motion using Newton's second law and solve it. First, let's examine all the forces acting on the system. Obviously, there is a restoring force, which follows Hooke's law, and which we discussed in the first video. Since we are considering damping, there is an additional force that we must take into account. The damping is, for example, due to the air resistance or friction. In all realistic situations, there is always some kind of damping present in the system. The question is how to model the damping force correctly. There are various models depending on the specific situation, but we won't go into the details of how many different kinds of damping forces there are. We will consider the simplest model where the damping force is proportional to the instantaneous velocity of the object expressed as the first time derivative of its position, like this. This makes sense when you think about it. When an object moves, for example, through air or water, the resistance that is exerted on the object by the medium, such as air molecules or water molecules, is greater the faster the object moves and vice versa. The constant gamma is just the coefficient needed to ensure the force has the correct physical units. Since this expression is a force, it must be measured in newtons, so the units of gamma must be measured in kilogram per second. This damping constant can be thought of as a property of the surrounding medium that the object is moving through. The larger the value of gamma, the larger the damping force, and vice versa. Of course, in reality, the damping force can depend on various factors, such as the shape of the object. For example, a needle experiences less resistance moving through air compared to a car, for example, simply because of its shape. Additionally, it should depend on the density of the medium, right? The denser the medium, the harder it is to move through. The resistance is greater when moving through water than moving through air, because water is denser than air. In this video, we will simplify things and only consider the specific case where the resisting force is proportional to the velocity of the object. This will simplify the math, but still capture the essential physics that we want to discuss, so we will work with this model. The negative sign here ensures that the resisting force always points in the correct direction. It must always act in the opposite direction to the instantaneous velocity, as can be seen in this animation. Now that we know all the forces acting on the system, we can immediately write down Newton's second law. It can be written in this form: mass times acceleration, expressed here as the second order time derivative of position with respect to time, and it equals the net force acting on the system, which in this case, the net force is the sum of the restoring force and the damping force. We can now move all the terms to the left-hand side of the equation and divide by mass. This gives us the equation of motion in this form. Similarly to the case of the simple harmonic oscillator, we introduce a new parameter called natural frequency of the oscillator measured in radians per second. We have already discussed its physical meaning. Essentially, it is the frequency of oscillation when the system is undamped. Alright, so solving this equation is actually quite straightforward. From a mathematical point of view, it is a second-order differential equation homogeneous with constant coefficients. We can solve it by first solving its characteristic equation, which can be written like this. And then we need to find its roots, that is, solve for lambda. The roots are easily found because this is a second-order polynomial equation of this type. Its roots can be found using the quadratic formula. It has two roots, one with a plus sign and the other with a minus sign. And in our case, if we compare the equation, the a is equal to 1, b is equal to gamma over m, and c is equal to the omega 0 squared. So we can immediately write down two solutions for lambda, one with plus sign and one with a negative sign here. Okay, now that we have found the roots, let's manipulate the expression a little bit to rewrite it in simple form. the expression under the square root will be denoted as omega prime. We choose the letter omega because this expression has the units of frequency again, and its physical meaning will be clear a little later. So we can rewrite the two lambdas as minus gamma over 2 times mass plus or minus omega prime. Now the solution of the system basically depends on omega prime. Notice that the expression under the square root here can be positive, 0, or negative, depending on the precise numerical values of gamma and omega 0. So 3 situations can occur. If the expression under the square root is positive, this situation is referred to as supercritical damping or overdamping. If it is 0, it is called critical damping, and if it's negative, it is referred to as subcritical damping or underdamping. Let's now focus and discuss all 3 cases separately. The first case we discuss is supercritical damping. In this case, the expression under the square root, or equivalently omega prime squared, is positive. This inequality can be expressed in this form. We see that the gamma over 2 times mass is greater than omega 0, which means that omega prime is a real number. The solution can then be written as a sum of real exponential functions. Before I show what this solution looks like on a graph, let's try to understand it intuitively. We have a prefactor here that is an exponentially decaying function of time due to the negative sign in the exponent. Notice that the exponent contains a gamma, the damping constant. The larger the value of the damping constant, the stronger the exponential decay. This prefactor multiplies 2 exponential real functions inside the parentheses. One of these has a negative exponent, which represents an exponentially decaying function, while the other has a positive exponent, which alone would tend to infinity as time increases. However, because it is multiplied by the decaying factor here, and given the condition we are working under, the decay is strong enough to overcome the exponential growth here. Therefore, we expect that the position will eventually decay to 0 as time goes on. Now let's look at the solution. I chose initial conditions where the system is initially at rest, and then I imposed the initial velocity in a positive x direction, leaving it to evolve afterward. The system starts moving in a positive x direction, reaches a maximum value, and then decays exponentially as time goes on. You might ask now obvious question, shouldn't the system oscillate around the equilibrium position? Not in this case, because the damping is too large. Although the system might naturally want to oscillate back and forth, the damping force is strong enough to prevent any oscillation. The second case is when the expression under the square root is 0. This happens when gamma over 2 times mass is equal to the omega 0. In this case, the solution is still exponentially decaying. Solution can be written in this form. We again have an exponentially decaying prefactor, and it multiplies a linearly increasing function of time. Eventually, the exponential decay dominates and the entire solution goes to 0 for a sufficiently long time, as shown in this animation. This situation is referred to as a critical damping. If the damping is too large, we get an exponentially decaying solution without oscillations until the damping reaches a critical value, expressed with this formula. When the damping is weaker than this critical value, the nature of solution changes again, and some oscillations will appear. This is the third and final case. The last case occurs when the expression under the square root is negative, or equivalently written as omega prime squared is lower than 0. This happens when gamma over 2 times mass is lower than natural frequency. Loosely speaking, when the damping is weak enough. There is a slight issue here. Negative value under the square root is only meaningful in a complex domain. So to address this, we'll first massage the expression for omega prime a bit. In the first step, I simply copied the expression for the omega prime. Then I rewrote it by placing a minus sign in front. Now we define the expression inside the parentheses as omega d squared, which is always positive by definition due to the condition we are considering. So we can write this expression by introducing the complex unit I. So the omega prime can be written as a plus or minus complex unit times omega d. So the solution can be written as a sum of 2 complex exponential multiplied by exponentially decaying prefactor. Let's discuss the nature of the solution. Let's step back a bit and recall the case with no damping, which we discussed in the previous video. When gamma is 0, the solution to the harmonic oscillator can be written as a sum of 2 complex exponentials, where omega 0 is natural frequency of the system. In the previous video, we argued that only the real part of this expression of this solution has the physical meaning, which represents the displacement of the object from equilibrium. In this case, the real part can be expressed, for example, with a cosine function, where the constant r is the amplitude of the oscillation and phi is the initial phase. Now, when we switch on the damping, that is when gamma is not equal to 0 and this inequality is satisfied, the solution can again be written as a sum of two complex exponentials, but with additional prefactor here. Once more, we can argue that only the real part of this expression has physical meaning, representing the displacement from equilibrium. Its real part can be written with a cosine function. Now, if you compare these two expressions, there are similarities. While in the undamped case, the amplitude remains constant and the system oscillates indefinitely with a frequency omega 0. In the case with the damping, the system oscillates with a frequency omega d, which is slightly less than the omega 0, and the amplitude is not constant in time, but decays exponentially over time. How fast does it decay? That depends on the gamma constant. The larger gamma is, the faster the decay. Conversely, a smaller gamma means a slower decay. This behavior is illustrated in the animation, where the oscillation gradually diminish in amplitude over time. This is exactly what happens in real systems, right? For example, if you set a mass on a spring into motion, it will initially oscillate, but due to friction or air resistance, the oscillations eventually stop. The energy is no longer conserved in the system, it is dissipated into the surroundings by the damping force. This is the last thing I want to show you. We have an oscillatory part of the solution expressed here with the cosine function, but it is modulated by an exponentially decaying amplitude, which is plotted here as this red line. Here is the comparison between two different values of the damping constant. The full line represents the smaller damping and the dashed lines represent the larger damping. So as we increase the damping, the solution decays to 0 much faster than with the smaller damping, as expected. That's it for today. I hope you enjoyed it, and if you like this video, please like and subscribe. Thank you.